All right, everybody, welcome back. This is the second video talking about numerical approximations to solutions of ODEs. And I told you last time that, or we showed last time that we had a method called the forward Euler method that gave us a sort of successive tangent line approximation to our solutions by means of a slope field. So we're using our slope fields to connect the dots between successive approximations of solutions to the differential equation. Now, it's not the most accurate thing in the world, but it is pretty good for starters. It's a really good starting point for numerical schemes. And the last thing I should say here is I kind of messed up in the last video. I said that was valid for n greater than or equal to 0. That should be for n greater than or equal to 1. So my apologies. But there it is. This is the forward Euler scheme. And we would like to approximate this guy. We would like to figure out what our how good this is at approximating solutions. So let me come back to this initial value problem up on top from our previous video. We wound up with a function. So I'm going to go ahead and create a function handle in here in MATLAB. And that's going to be 3 minus twice t minus 1/2 times y. So I get a function handle out of this guy. Let me go ahead and type that in so you can see. I can create a function handle. That way I can keep feeding it whatever inputs I want. I'm going to use t0 equals 0 because that's what it's supposed to be based on this initial, this initialization. And this next step, we can go ahead and choose however long a time we want to approximate this solution. And I'm going to go ahead and say, let's just go ahead and approximate this out until t equals 5. Okay, so we're going to go ahead and assign that. And we're going to create a vector here. Just t vector, not t-span. T is going to be the vector, and I'm going to create a column vector out of this in a moment, so I'll leave that off so you can see it. So from t0, we're going to skip by, I don't know, maybe 0.05. Let's go crazy, 0.05 because we're in a computer. So we're going to skip by 0.05, so I need a colon. And then we're going to go up until t. Great. And so I should go ahead and assign h equals 0.005. So there's my step size. So this is a very long vector. We really don't want to have to be doing this computation over and over and over again by hand. So what we're going to do is instead we're going to let the computer try to make this computation for us. So I'm going to go ahead and ask for what the length of my t vector is. Okay, 1001. Great. Y is going to be a matrix of 0 or vector of zeros of the same length as t. And we're going to assign to the first element there in y the initial condition. So y of 1 should be 1 based on our initial value problem. What do you mean you don't recognize y0? Did I not say y0 is equal to 1? I may have typed it in wrong upstairs. I'm not going to go look and find out. But now, there it is. Oh, son of a gun. Y of 1 equals 1. And it's just going to go ahead and spit out the whole thing. So let me go ahead and clear the screen. So CLC, clear command prompt. And we're going to go ahead and create a for loop where I goes from 1 up to n minus 1. Okay, I'm going out to n minus 1 because my vector is not, because of the way I'm going to create my iteration scheme here, right? The next iteration, so the next approximation of y is going to be based on what the current one is, plus what the approximation of the current slope is, or what the slope currently is, y of I as well, and we're going to step forward by h. And we're going to end that loop, and that created this entire vector y. And look at that, it did that in 3 lines of code. Check it out. I can go ahead and plot the solution here, and I'll do that in blue because why not? And have a look. I have a pretty little solution curve. Now, the real question, is this actually close to what the real solution looks like? And we know how to solve this guy. We actually can solve this. I believe if you use you have to use first order linear, so you have to use an integrating factor. But when you do, you wind up with 14 minus 4t. Is that plus? No, it's minus 13e to the minus t over 2. Right, go ahead and verify that on your own, but let me show you what this looks like in the computer. Y now is going to be exactly that scheme. So big Y now is 4 times t minus 13 times, okay, so little e is not defined in the computer. We actually have to use the exponential function itself to create this, this function, or at least in MATLAB, that's what you have to do. Great, so we've created this guy. Let's go ahead and plot ty in blue and then t big Y. Let's do that guy in red. And sure enough, whoa, okay, I made a mistake somewhere. Where did I make my mistake? What was the solution? Minus 4t minus 13 times e to the minus 2t. Did I type in my f function correctly? Let me ask MATLAB. Or ask the viewers. 3 minus 2t. Oh, yeah, that's what happened. So f now at t by y, 3 minus 2 star t minus 1 over 2, not 1.2 times y. There's my new function handle. We run this scheme one more time. 1 to n minus 1 y of I plus 1 is y of I plus new f of t of I, y of I. I'm wondering if I should zero that guy out. No, because I'm using the same initial condition. Okay, plot t by y should give me something that looks vaguely familiar. Yeah, vaguely similar. Okay, and let's go ahead and plot ty in blue and then t big Y in red, and with any luck, they now overlap. And that looks like it's pretty spot on here. I could even plot the error for you. So error, let's go ahead and take the absolute value of, this will be y minus big Y. And we can go ahead and plot t by and that will give us the following error. So this is actually a very small error. Notice this 10 to the minus 3 in the top left. This is actually, these solutions are in really good agreement until, let me go back here. So go up, 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 there we go. Notice that the place where the solutions don't really agree that well is up here where the solutions are curving a lot. So let's see if I can't zoom in. So notice there's a fair bit of separation. Let me bring that back down. There's a fair bit of separation between the curves here, and that's reflected in this this error plot. So plot t by error again, and you can see that's exactly where we see the most error. The error starts to come back down once our plot starts to look like a line again, and that's exactly what we see in our solution over here, right? That this exponential piece starts to decay away, and we start to look more and more like a line, and the approximation scheme is based on the tangent line, so that should be a really good approximation when the function is approximately linear. So this actually is a really great way of approximating functions, at least on the small scale. Let me show you what happens if we change this up a little bit. So let me clear all real quick. We're going to change up the step size. So what happens if the step size isn't so small? H equals 1 now, and we're going to go ahead and create t again. So from t0 by h out to t. So this is really only going to be all. Okay, so I have to redefine t0. That's 0. So t equals t0 by h out to t. Okay, it doesn't know what big T is either. That was my fault. Big T is 5. There we go. Let's try this one more time. There it is. And we're going to turn that into a column vector. Great. Y is now going to be a 6 by 1 vector of zeros. N is going to be 6. And we're going to go ahead and create our for loop again. So 1 out to n minus 1. yi plus 1 is equal to y by I plus f of the current location, so tii by yii, and we're going to multiply that by h. And remember, h is the thing that's different here. H is now much larger. Oh, shame, I didn't create my function handle, because I should just not use clear all ever. So 3 minus 2 star t, let's see if I can get it right this time, 1 over 2 times y. Okay, cool. And now we go ahead and run this guy one more time. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. And now we can plot again, t by y. And look how rigid that is. This is a very, very rigid polygonal curve. And we know how terrible the solution is going to be here. So I'm going to go ahead and create a new vector, s, and we'll make this just a linspace from 0 to 5. Yeah, and we'll do this by like, I don't know, maybe 1,000 points, just because we can. Then big Y is going to go ahead and be the same function from before. So 14 minus 4s now, minus 13 times the exponential function minus s over 2. Let's go ahead and plot these guys together, and you're going to love how terrible this looks. It is just god-awful. This is what happens when you don't use the correct step size. Actually, this looks like what happens when you don't use the correct initial condition. So let's make sure we did this right. Y of 1 should be 1. And now we're going to run that scheme one more time. For I goes from 1 to n minus 1. yi plus 1 is yii plus, not equals, f of tii by yii star. That is, yep, over. And then now we can try to do this one more time with the correct scheme, and voila! It started out at the same location, but man, this thing curved away real quick. Remember, the red solution is the exact solution, right? This is the exact correct function. So notice, if you use a step size that is too large, you're going to be accruing potentially a large error between your current your approximation and the correct value. So when you're using these approximation schemes, you have to use a fairly small step size. There's a whole theory behind how to choose that step size so that you're not making too many computations and still be fairly accurate. That is a class on numerical analysis, and depending on demand, I may create a series, a lecture series based on that as well. So let me know down in the comments if you feel like doing some numerical analysis as well. But that is, I believe, where we are going to end for right now. Our foray into, oh shoot, come on, our foray into numerical approximation schemes. So let me go ahead and not that, I want this, and then we'll bring up that, and then that. Whew. Now everything is right in the world. Okay, great. And this is, if you feel like pausing the video, and then I'll zoom in a little bit more for you. This is straight out of the textbook reference that I'm using. But this is exactly what you would see for a different step size. So for our example step size that we did up here, that is exactly what we wind up with as an approximation. And this thing overshoots like crazy. So this is your introduction into numerical analysis. And there are definitely more approximation schemes, better approximation schemes than forward Euler. Forward Euler is not the most stable approximation scheme. You will be jumping around a lot onto a whole bunch of different solutions to the same ODE. And that's because solutions to ODEs are not necessarily lines. So that means that however small a step size you take, you are moving on to a different solution of the ODE or another solution of the ODE for a different initial value, potentially. And yeah, not potentially, almost guaranteed you're on a different solution. So be aware that this is, at best, an approximation, and it's not going to be able to approximate your solution for a very long interval of time. But if you're looking at in a very small neighborhood, it does an exceptionally good job of tracking that error. So I think that's about all I want to say on the matter here. The next section, we're going to take one more stab at pure math, just to show you exactly how we come up with this existence and uniqueness theorem from basic principles. Like we will give a proof. So feel free to skip it on a first pass and come back to it later. But I'm going to go ahead and make the video for this next section, and you can feel free to skip on.